In this tutorial, we have seen lots of examples that self-supervised model is very powerful. We know that self-supervised model is very powerful in speech recognition and a wide variety of different speech processing tasks. And in this part, I'm going to talk about something beyond accuracy. So besides accuracy, we also cared about other factors of self-supervised learning. So here, I'm going to talk about 4 topics. The first one is how to use the self-supervised model in an efficient way. So this is the most typical way to use the self-supervised model. You concatenate the self-supervised model with the downstream model, and you train both the downstream model and self-supervised model jointly. You train downstream model and self-supervised model end-to-end. The weakness of this approach is if we fine-tune the self-supervised model for each task, then we have to store a new set of parameters for each task. So for each task, we will have a new set of parameters in the self-supervised model. So for each task, we need a large memory to store a whole self-supervised model. And if you have a large amount of tasks, this way may be intractable. Another way to leverage self-supervised model is consider them as feature extractor. So the parameter of the self-supervised model is always fixed when you use them in the downstream task. You only train the downstream model and fix the parameter of the self-supervised model. If you use self-supervised learning in this way, you only have to store one self-supervised model for all the different tasks. So even though you want to add more tasks, you don't need more parameters for your self-supervised model. You only need one model for all the different tasks. And there are different ways to use the self-supervised model as a feature extractor. One most intuitive way is use the last layer of the self-supervised model as the input of the downstream model. You take the output of the last layer of a self-supervised model as the input of the downstream model. However, based on the previous experiments on Superb, we found that this approach do not always lead to decent performance on the Superb benchmark. We found that if we only take the last layer as the input of the downstream model, usually the large model, for example, Hilbert large, Web2Vec large, they would have very poor performance, even worse than typical acoustic feature like FBAC. And we found that with only using the last layer, most self-supervised models do not work well on speaker verification. And this is probably because different layers contain different information. Only take the last layer as the input of the downstream task is not sufficient. To better use the self-supervised model as a feature extractor, there's another way to leverage self-supervised model. You still fix the parameter of self-supervised model, but you weighted some the output of all the different layers. So here, as shown in this figure, we weighted some all the representation from different layers and obtain a set of new representation. And the downstream model takes the results of weighted sum as input. The weights used in the weighted sum are jointly learned with the downstream model. So in different tasks, downstream model can automatically learn the weights, and different layers can have different weights. The downstream model can select the proper weight for a specific layer based on the characteristic of the task, and different tasks would have different weights. So this is another more efficient way to use the self-supervised model as a feature extractor. Another way to use self-supervised model is based on adapter. What is the adapter? Adapter is a small module inserted into cell-supervised model. When you use the adapter, the parameters in the original cell-supervised model is still fixed, and you only learn the inserted adapter. You only learn the parameter in the adapters. An adapter is not a new idea in natural language processing. The idea of adapter has been widely studied in natural language processing, and you can visit a web page called Adapter Hub and find all variety of adapters used in the TextBird. If we use adapter, then for all the different tasks, you only have to store the parameter in an adapter for a task. So you do not have to store the whole cell-supervised model for a task. For each task, you only have to store an adapter. So this can minimize the requirement of the memory you need to use if you want to solve a wide range of different tasks. Adapters have been widely used in natural language processing. Then how about speech processing? There's a paper about using adapter for speech cell-supervised model. And this is the result from the paper. The vertical axis is word error rate, and the horizontal axis is the number of parameters you need to train for a specific task. And you can find that if you fine-tune the whole layer, the blue curve is the result you will obtain. And if you use adapter, the red curve is the result you obtain. You can find that if you use adapter, you can use much less parameter to achieve the same performance as fine-tune the whole model. Besides adapter, there's another way to use cell-supervised model. You can use prompt, or this idea some people also call it reprogramming. You can use prompt or reprogramming to control the cell-supervised model. So here in the prompting approach, the cell-supervised model is always fixed. You only use one set of parameters to solve all the different tasks. The model is always fixed. The only change is the input. You give a cell-supervised model different input, and it will act differently and solve different tasks. The extra input you add to control the cell-supervised model is called prompt. By adding different prompt, the cell-supervised model can solve different tasks. This is the basic idea of prompting.
Prompting is not a new idea in natural language processing. You can check this webpage to find a large collection of papers about using prompting for natural language processing. For speech, the idea of reprogramming has been used on voice command models. It is possible to reprogram voice command model for time series classification. It is also possible to reprogram voice command models for different languages.
In cell-supervised speech learning, there is an attempt to prompt GSLM, Generated Spoken Language Model. So it is possible to prompt GSLM to make GSLM solve different speech processing tasks. We have introduced GSLM in the previous part. So GSLM is a language model, and this language model is trained on the output of cell-supervised representation model, for example, Hubert. So Hubert can output token sequence as pseudotext, and GSLM is trained on pseudotext. So how to use GSLM on different tasks? How can we prompt GSLM? So without fine-tune its parameter, we can use GSLM in different tasks. So in our scenario, both Hubert and GSLM, they are fixed. Their parameters are fixed. They are used across all the different tasks. And let's say we are going to prompt GSLN for speech recognition. Then we have to create a mapping table. And let's say we are going to working on character-based ASR. So our mapping table will map each character to Hubert's token ID. So for example, A mapped to ID 1, B mapped to 2, C mapped to 3, and so on. And end of sentence mapped to 100. Then we have a training data, the utterance, and its manual transcription. The manual transcription of this utterance is kept. And Hubert takes this utterance as input and generate a token sequence. GSLN will take the token sequence as input. And we put some prompt. The prompt is a sequence of vectors in front of the token sequence. And the prompt is trainable. The training target of Rho's prompt is to make the GSLN generate the correct transcription. For example, the first character in the manual transcription is C. Then GSLN have to output token number 3 because token number 3 mapped to character C. Then the second character is A here. Then the GSLN has to output 1, so 1 will be mapped to A. Then GSLN will output token number 20. Then token number 20 will map to the character T. And finally, GSLN has to output token number 100. It makes to end of sentence. So we train the prompt to make GSLN generate the desired output. By this framework, we can prompt GSLN for any speech processing task if the task can be formulated as sequence-to-sequence model. I know this idea sounds a little bit crazy. Can we really add some embedding in front of the token sequence to make GSLN do speech recognition? You can read the reference to see whether this is possible. There's also some paper using idea of prompting to solve the problem of spoken language processing. There is EmoBird, solve the problem of emotion recognition in the scenario of multi-modeling with the idea of prompt. And recently, there's another paper of WebPrompt, which used the prompting idea to deal with spoken language understanding. I put the reference here for your consideration. The next topic is the security issue of self-supervised learning. As you know, in the future, we will use a self-supervised model for a wide range of downstream tasks. We already see the paradigm that a self-supervised model can be used in a wide range of different tasks. Because we use self-supervised model for many different applications, the self-supervised model play a very critical role. Would it become single point of failure? There's a research about adversarial attack on self-supervised model. In adversarial attack, you have a self-supervised model. Today, usually self-supervised model are public available. So you have a self-supervised model. Then we try to add small noise on the input of the self-supervised model. And the small noise will make the output of the self-supervised model very different from its original output. So given this signal, this is the original output, then we add a very small signal to this input. And we try to make the self-supervised model has a very different output from its original output. Then we can add this attack signal to the self-supervised model to make it have very different output. And because the output is different, probably all the downstream tasks leverage this self-supervised model will have catastrophic performance degradation. And in this paper, the experimental results show that it is easily the self-supervised model can be attacked. In the black box setting, those downstream model, their performance degrade very seriously. This is about adversarial attack. And we also consider privacy attack. So as you know, self-supervised model is learned from a large collection of audio data. And probably those data can come from real application. Although the customer can ask the service provider to delete their voice for the privacy reason. However, is it possible to recover speech signal from the self-supervised model? If someone can access to the self-supervised model, is it possible to recover the training data of self-supervised model? If this is possible, then there is still some privacy leakage issue for self-supervised model. Fortunately, until now, I haven't seen any research successfully recover the training data from the parameter of self-supervised model. So we can feel a little bit relaxed. It looks like privacy attack is not that easy to self-supervised model. However, another type of attack worked pretty well. We found that membership inference attack can successfully attack the self-supervised model. What is membership inference attack? In membership inference attack, the goal is we have to identify an utterance is in the training set or not. For example, given an utterance, the green one, it is in the training data, so the attacker have to say yes, and given another utterance not in the training data, the attacker have to say no, this is not in the training set, and this is in the training set. And in the literature, this paper show that membership inference attack is very easy. It is very easy to know that an utterance is in the training set of a self-supervised model or not. You can check this paper to find how they do it. And we want to know the inference of data bias to self-supervised model. The self-supervised model is trained from unlabeled audio data. Unlabeled audio data can be easily collected from the internet. However, if the collection process is automatically, then the data can be biased in different ways. For example, the collected data can be gender bias or accent bias, or probably the collected data can only contain some specific topic and missing some other topics. Or probably the speaking rate of the collected data can be higher or lower than normal. They are all kinds of different bias. Does the bias data influence the SSL model's performance on the downstream tasks? There is some research about the influence of data bias to self-supervised model. One is the influence of speaking rate to the self-supervised model. There is a paper studying the influence of speaking rate to the self-supervised model. And the researchers found that self-supervised model pre-trained on speech with faster speaking rate obtain worse performance. On the other hand, lower speaking rate does not degrade performance. So if you speak to the self-supervised model slowly, it's fine. But you speak faster to the self-supervised model, then it learns poorly. And there's some paper about gender bias. So if you train a gender-specific model, intuitively, the gender-specific model leads to overall worse performance on gender-balanced testing set. However, this is only for fine-tuning. If you fine-tune your self-supervised model with the downstream task, then gender-specific model degrade the performance. However, the conclusion is mixed when the self-supervised model serves as feature extractor. If the self-supervised model are used as feature extractor, gender-specific model do not especially degrade the performance compared with gender-balanced model. And there is also some study about language bias. The results show that SSL model has very small native language effect. And this explains why the Web2Vec trained on monolingual data can be easily generalized to several languages. Even though it's trained from one language, it can easily apply on multiple languages. This is probably because it has small language effect, small native language effect. Today, usually people try to train larger and larger self-supervised model. But on the other hand, can we compress those self-supervised model? As you know, larger self-supervised model usually lead to better results. This is some results from the SUPERB benchmark on intent classification. The horizontal axis is the number of parameters in self-supervised model. With larger model, you get higher intent classification accuracy. For speaker identification, the situation is very similar with larger model, higher accuracy. On speech recognition, larger model, better performance, lower error rate. So larger self-supervised model lead to better performance. However, we want to have the greener model. We want to see whether we can have small model it can run on device. And there are many typical ways to compress a model. And the researchers try to use those approach to compress self-supervised model. People have tried knowledge distillation. I believe most of you are familiar with knowledge distillation. In knowledge distillation, you have a large model as the teacher model and a smaller model as the student model. And the student model, and during knowledge distillation, you want the teacher model and student model have similar output. However, we found that if we only apply non-typical knowledge distillation, this approach do not always get good performance on all the tasks. For example, typical knowledge distillation do not work well on speaker identification. So in this experiment, we compress Hilbert by knowledge distillation, so we have a smaller Hilbert. We found that if we compare the performance of the original Hilbert and the smaller Hilbert, the performance degrades seriously. This is because each layer in the self-supervised model contains different information. Learn from only the last layer is not sufficient. So there's another approach for knowledge distillation, which is called Distill-Hilbert. In Distill-Hilbert, the model has multiple heads. Each head tries to learn from one layer of the teacher model. For example, this head learns from the 4th layer of the teacher model. This head learns from the 12th layer of the teacher model. With this kind of design, the Distill-Hilbert can learn from the multiple layers of its teacher Hilbert. And this is the result of Distill-Hilbert. You can find that on intent classification and speaker identification, Distill-Hilbert is much smaller than Hilbert. If you compare the horizontal line, you can find that the Distill-Hilbert have 25% parameter of the original Hilbert. And the performance on intent classification and speaker identification are very close to the original Hilbert. However, network compression harms the speech recognition. So the performance of Distill-Hilbert is worse than the original Hilbert. However, the Distill-Hilbert still outperforms other models which have the same amount of parameters. Besides knowledge distillation, Pruning is another very standard way to compress your network. In the paper Prune, Adjust, Reprune, PARP, the authors found that there are subnetworks in Web2Vec 2.0 that can achieve absolute 10 to 12% word error rate decrease compared with the full model. This is very surprising. Usually when you prune your model, well, your model, the performance is usually decreased, just more or less. However, there's some approach that not only keep the performance, but actually improve the performance after pruning. So you can read the paper for more details. There's another model called Lightweight-Huber. Lightweight-Huber uses knowledge distillation as Distill-Huber. It used knowledge distillation to train a student model, and it used an approach called once-for-all training to make the model even more smaller. You can consider once-for-all training as a special way to do network pruning. So Lightweight-Huber used both knowledge distillation and the pruning approach. And Lightweight-Huber get very good performance. It obtained comparable performance to the Huber teacher in most tests. For example, in ASR, Lightweight-Huber has almost the same model size as Distill-Huber, but its performance is closer to its Huber teacher.